inkjet, you have the thin film transistors, 3D printing, printed electrochemical sensor, gravure printed.
On. Okay, check Dr. Hafiz.
Sekejap. Dengar tak suara?
Dengar? Suara dengar?
Clear lah.
Clear. Nak try slide tak?
Nak try slide sekejap. Try window. Window kan. Nampak tak?
Nampak. Cuma gerak-gerak.
Wow. Okay.
Nak wow sangat.
Orang lain
Yalah.
Orang lain tengoklah.
Tak apa. Okay.
Kenapa tak boleh ni? Kenapa tak boleh connect chat? Kejap Kena ni lah.
Dengar kita tak?
Dengar?
Kita unmute ganggu tak? Ada bunyi daripada kita yang ni ke?
Apa dia?
Sebab kita ingat kita nak stay unmute je. Dr. John ada kan?
Ada pun.
Bukan, dah contact dia kan?
JC Juan Okay, nak hantar ni tak? Revolution form. Dr. John, Dr. Rahul, Dr. Hi Miss. Nak try tu?
Hi.
Nak try. Mic.
Hello. Dengar tak?
Dengar.
Clear? Okay. Right. Wait.
Nak try screen.
Nak try present.
Apa boleh?
Nampak ke?
Okay, nampak.
Kalau saya buat macam ni kan, dia nampak kecil. I mean like 2 window kiri kanan.
Tak, nampak yang ni je.
Oh, nampak yang ni je?
Sebab share window yang ni je kan? Nampak yang ni je. Tapi cuba tu apa? Yang ni presentation presentation mode.
Kejap. Oh, okay, sekejap. Okay, nampak kan? Kalau ni presentation.
Okay.
Alright.
Okay.
Hello, morning. So please welcome to our session today. So this is our parallel session 4 under the chemical reactions engineering. So today we have 1, 2, 3, 4 speakers. Okay, I'm Dr. Juan from Nanotechnology University Malaya. We have 4 speakers. Of these 4, 2 of them are invited speakers. Without further ado, we'd like to invite Miss Idiana Shahira binti Abdul Ghani to share her works on various synthesis methods of sulfonated titanium oxide catalyst for esterification of PFAD feedstock into biodiesel. So, Miss No Adina, the floor is yours. Thank you.
Hi, Assalamualaikum and good morning everyone. First of all, I would like to share my screen first.
Yep, you can see your screens.
Hold on. Is it in
Yep.
presentation mode? Alright.
Yes. It's in the
Okay.
presentation mode. Yeah, nice and clear. You can
Alright.
go ahead when you are ready. Thanks.
Okay. Thank you, Dr. Jan. Once again, good morning and hi everyone. My name is Nur Irdina Shahira binti Abdul Ghani. I am from University Technology Mara. So today I would like to present about my research work, which is various synthesis methods of SNO2, which is tin oxide catalyst for esterification of FAD feedstock into biodiesel. So the content for this presentation is including introduction, methodology, results, and discussion, also conclusion. For the introduction, as for the background of study, the research is conducted due to how we can say that the global greenhouse gas emission has shown that the energy has contributed 73.2% of GHG gas emissions, which is 16.2% of it from transport. And from the Malaysia Energy Information, it shows that 38% and 33% consumption is from the source of oil and gas. And also from the US Energy Information Administration shows that 37% are usable on petroleum and other liquids. So it is estimated that oil and gas reserve will last only for the next 15 and 30 years respectively. This is the source from petroleum. And the usage of petroleum-based fuel contributes to carcinogenic influence on the ecosystem. So the study, including to convert from feedstocks, we have the various feedstock which include edible and non-edible oil, with the reaction of trans-esterification or esterification to convert into biodiesel with the aid of catalyst. Next is about the comparison of chemical structure. Here we can see that the current petrodiesel is non-renewable energy, non-biodegradable, and higher emission of CO2, and also not environmental friendly, as I mentioned earlier. So on what we have on my study is going to produce the biodiesel. So the comparison of few properties we can see here, that the composition is way and much better as compared to petrodiesel, which is the current diesel that we use now. So for the feedstock, this study is converting palm fatty acid distillate, which is the waste product from the refinery of crude palm oil, as you can see here. Which will convert it to from the crude palm oil, go through the refining, and it produces palm fatty acid distillate. So we take the waste to convert into the biodiesel. So mainly the FFA or free fatty acid content in the PFAD is measuring on palmitic acid, which is at 72.7 to 92.6%. So the catalyst for esterification, we have including the previous study and also the current study, we have two types of major catalysts, which is homogeneous and heterogeneous. Despite of all these, what we call the advantages of homogeneous, they have two weaknesses in comparing to the heterogeneous, which is acid homogeneous catalysts cause difficulty in post-treatment and corrosion of system equipment, and the expensive recycling leads to high consumption and inefficient in terms of cost of production this biodiesel. So the SiO2 acid active site could be enhanced using sulfonation acid activation treatment, and to fully anchor the sulfonated anions on the SiO2 surface, various methods of synthesis has been used. So for the methodology, here is the overview for the synthesis of catalyst. The first one, we have method from solid state. The second one is sol gel. The third one is self-propagating combustions. All of these three catalysts that has been synthesized, we're going to do the sulfonation acid activation treatment using the chlorosulfonic acid, which is much and way more better as compared to the other acid, and it is reported the chlorosulfonic acid is one of the high acidity type of acid. So the catalyst of tin oxide is characterized by using 5 different instruments. The first one is simultaneous thermogravimetric analyzer STA, which is to measure both weight loss and heat flow of precursor. The XRD or X-ray diffraction to identify the purity and crystalline properties of catalyst. The third one is BET to determine the textural properties of catalyst. The fourth one is field emission scanning electron microscopy integrated with energy dispersive of X-ray FISM EDX to determine the surface morphology and elemental composition of catalyst. And the fifth one is temperature programmed desorption of ammonia, TPD, and H3 to study the acidity properties of catalyst. So the catalytic acidification of PFAD into biodiesel, in this study, I was only doing for the catalyst screening. So this is how it looks like. For the reaction of acidification, I'm using the identical condition based on the previous studies, which include of PFAD, which include the condition from methanol to oil ratio, catalyst loading, temperature, and time. So, yeah. For the results and discussion, for the characterization of catalyst from STA, we can see from these three graphs, this is from solid state, tin oxide. This is precursor tin oxide solid state, sol gel, and also SPC. So below 500 degrees Celsius, the loss rate ascribed to moisture is reported. Loss rate ascribed to moisture evaporation, organic traces removal, and precursor decomposition to its oxide form. So from the three synthesis methods show no significant weight loss after 400 degrees Celsius, and thus all the catalysts were calcined at 600 degrees Celsius for 6 hours to give the pure single phase of tin oxide before proceed with acid treatment. So this one is the XRD phase analysis. We can compare the first graph is the pattern XRD patterns of non-sulfonated, while the B graph is indicates the sulfonated tin oxide catalyst. This one is thermal decomposition. This one is solid state, sol gel method, and also SPC. All of these non-sulfonated shows high intensity of XRD peaks except for the solid state method. That indicates it has the lowest crystalline due to no heat applied during the reaction, because during the reaction of synthesis, the low temperature, no high temperature is used, and then the crystallinity increase when increasing the use reaction temperature, 50 degrees Celsius for sol gel method and 350 degrees Celsius for SPC method, self-propagating combustion. So the meaning is increase the reaction temperature, give resulting in increasing the crystal growth rate. Next one is about the BET. As you can see here, the BET non-sulfonated catalyst is greater than sulfonated. So from this, we can conclude that SnO2 SPC gives highest BET reduction, about 73.3%, followed by sol gel and also solid state. This also indicates that sulfonated tin oxide SPC catalyst anchored with many ions and sulfonic ions and become more acidic. So the sulfonic ions have greater tendency to be located inside the pores and block it. So this is the surface area and porosity of the BET. This one, the white one indicates the non-sulfonated SnO2 nanocatalyst, while the yellow one indicates sulfonated. From this, that the non-sulfonated and sulfonated SnO2 catalysts were formed in the presence of two phases, which the first phase consists of large irregular. For the FISM EDX shows that the non-sulfonated form into two phases. This one is the first phase consists of large irregular particles, and the second one shows a new crystalline phase. This indicates that the sulfonated SnO2 SPC is the best one from the FISM EDX. For the acidity properties, initially it indicates that sulfonated SnO2 catalyst increase of total acid density due to existence of sulfonic ion that enhance the catalyst acidity, which indicates that also the SnO2 SPC sulfonated method exhibit highest acid density in strong acidic region. This is essential for the effect of electron drawing from the sulfonic group that modify the acidity of SnO2 catalyst. So the catalyst screening shows that the highest FFA conversion from PFAD feedstock to the biodiesel is from SPC method at 86.9% conversion, which also sulfonated SnO2 SPC. So for the conclusion, different synthesis methods exhibit different properties. Among all the synthesis methods, the sulfonated SnO2 synthesis from SPC showed the most FFA conversion. The greatest benefits of sulfonated was its stability per cell in catalyst preparation and is the catalyst separation from the product. So the selection of synthesis method is crucial in designing an active catalyst to reduce the cost of biodiesel production in terms of low value, cheaper, abundant, and also non-edible of PFAD feedstock. So that's all from me. Thank you.
Thank you very much, Diana. So I open to the participants to ask questions, if any. Let me check the check box. Any questions? Do you have any questions? Thank you, Adina, for very interesting presentations.
Thank you.
Yep. So next, move to next speaker, Mr. Lim Hong Hua. He will present a talk entitled Synthesis of Carbide Lime-Based Derived Base Catalyst, KF/CLW iron oxide for methyl ester productions and optimization study. Mr. Lim, the floor is yours. So you can present whenever you are ready. Reminder to the speaker, you are given 50 minutes for presentation and 5-minute Q&A. Thank you. Can you are mute, Miss Lim? Okay. Now yes, we can hear you now. Okay, awesome. Okay. Yep. Go ahead, please.
Good day to everyone. My name is Vipong Hua. Today I would like to present our project about the synthesis of carbide waste derived base catalyst KFClWfe3O4 for metal ester production and optimization study. The outline for the presentation today will be research background, project objective, methodology, result and discussion, conclusion, and acknowledgement. First, I would like to talk about the research background. Nowadays, renewable energy is getting more and more important due to the energy consumption is getting higher and higher every year. The energy consumption is getting higher due to the modernization and the industrialization. The mass consumption, especially the mass consumption of the fossil fuels. The mass consumption of the fossil fuel has causing a lot of environment problems like the climate change or the greenhouse effect. That's why renewable energy is very important now. There are many types of renewable energy, such as solar, wind, biomass, geothermal, and hydroelectric energy. Now for our project today, I would like to talk more about the biomass, especially the biodiesel. What is biodiesel? Biodiesel is defined as the organic fuel that is made from the natural elements, such as the animal oils or the plant oils. Next, I would like to explain about the carbide line. Carbide line is the material that we will use for the production of the catalyst. The catalyst that produced for the carbide line will be used for the production of the biodiesel. Carbide line is the byproduct of the acetylene gas production through hydrolysis of the calcium carbonate. It is high in calcium content, like it contains 85 to 95% of the calcium hydroxide, 1 to 10% of the calcium carbonate, and 1 to 3% of the unreacted carbon and silicate. It is confirmed the calcium-rich component has high base characteristic, which will help to speed up the biodiesel process if it is used as a catalyst. Next is the catalyst. Catalyst is the substance that will be used for the transesterification of the methanol with the oil. It will speed up the production of the biodiesel. There are two types of catalyst. One is heterogeneous catalyst and one is homogeneous catalyst. In our project, we will more focus on the heterogeneous catalyst, especially the best heterogeneous catalyst. What is the difference between the heterogeneous and the homogeneous catalyst? Heterogeneous catalyst is the catalyst that is in different phase as the substance reacting. As you can see from the pictures, the catalyst is in solid phase, while the substance reacting is in the liquid phase. For the homogeneous catalyst, the catalyst is in the same phase as the substance reacting. From the picture, you can see catalyst and the substance reacting both are in liquid phase. Now I would like to explain the biodiesel production. When the oil plus mixed with the methanol, it will undergo the esterification with the presence of the base catalyst. So it will form the biodiesel and glycerol as the product. This is the molecular formula for the production for the transesterification reaction. The catalyst is added to increase the reaction between the oil and methanol, and it also can help to produce higher yield of the biodiesel in short time. For the purpose statement, usually the carbide sludge in the industrial, it will be washed into the settling pots, and it will create a line mark, and it create the difficulties for the utilization, and it will cause a lot of problem for the environment. The characteristic for the carbide lime, such as high alkalinity, unpleasant odor, irritation to skin and throats, will cause severe difficulty for the handling. The conventional way of production of biodiesel is catalyzed by homogeneous acid or base, such as sulfuric acid or sodium hydroxide. Homogeneous catalysts are quite corrosive and it's very hard to remove from the product, and it will cause a lot of waste washing water generated. So the objective of this project is to investigate the potential of the carbide lime as catalyst in the biodiesel production, and to prepare a strong base catalyst KFClWFE304 from the carbide lime waste for the production of the biodiesel, and to investigate the effects of the reaction times, methanol and oil ratio, and catalyst loading on the biodiesel production by using the Taguchi method. Now, I would like to explain the methodology they use for the project. First is the catalyst preparations. In order to produce the ClWFE304, we need to produce the Fe304 first. When the iron 2 sulfate hydrate mixed with the iron 3 sulfate hydrate, then the product of these two we mix with the 20% ammonia solution and etch for 1 hour. After that, we will wash the black precipitation with distilled water and dry it for 1 day. This is the process to produce the Fe304. Next, the carbide lime will be oven dry and calcined at 850 degrees Celsius for 4 hours. Then the calcined product will mix with the Fe304 produced previously and impregnate it with 25% of the KF, oven dry and calcined at 600 degrees Celsius for 3 hours. And last, the KFClWFE304 will be produced, and it will undergo the morphology analysis, structure analysis, base strength analysis, and elemental analysis. Next, the catalyst produced will be used for the esterifications. The palm oil will mix with the methanol with the presence of the catalyst produced before. Then it will produce the biodiesel and the glycerol. The final product produced from the esterification will be poured into the separation funnel in order for us to separate the biodiesel and the glycerol easily. Then I would like to present about the result and the discussion from this project. First is the best strength analysis. The best strength of the catalyst was determined by the Hammond indicator. As you can see, the best strength of the carbide lime is until the phenolphthalein. The best strength is 9.3. The original color of the phenolphthalein changed from colorless to pink. While for the KFClWFE304, it falls under the diphenylamine, which the best strength is 22.3. The diphenylamine changed from the colorless into dark blue. So it means the KSClWFE304 have the best strength of 22.3. Next, the basicity of the catalyst was determined by temperature program desorption of carbon dioxide to observe the dissolved molecules from the surface of the catalyst when the temperature increased. As you can see from the graph, the desorption peak for both carbide lime waste and the KFClWFE304 occur at 819 degrees Celsius. Carbide lime waste has the basic site of 88.4375 micromole per gram, while KFClWFE304 has the basic site of 1775.67 micromole per gram. It means in the basic site of the KSClWFE304 and carbide lime is in good agreement with the Hammond indicator tested before. Next is the morphology analysis. The morphology of the carbon waste, as you can see from the picture, was uneven and irregular in particle shape. While for the KFCRW Fe2O4, the catalyst agglomerate and form into a large crystal structure due to the impregnation of the KF. It also composed of small spherical grains and have porous structure. Next is the structural and BT surface area analysis. The structural analysis was conducted by using the X-ray diffraction to obtain the information about the catalyst and identify the compounds based on their diffraction peak. For the KFCRWFE2O4, from the picture, it can be seen that CaOH2 was the dominant compound based on the database ICSD98005886. Next is the Fe2O4 based on the database ICSD9801111045. Then the last one is H2, ICSD9800211882. For the BT of the surface area of the KFCRWFE2O4 catalyst was 1.77 meter square per gram. Then is the elemental analysis. The EDX spectrum shows that the surface of the catalyst is mostly made up of Ca, K, F, and O with the molar ratio of 1, 2.92, 3.36, and 6.55. Then I would like to explain the optimization study. First is the SN ratio analysis. The optimization parameter designed by using the Taguchi method L9 in orthogonal array. The methanol from the result, it shows that methanol to oil molar ratio has a high value of SN ratio, followed by the catalyst loading and the reaction time. The methyl ester production increased with the increasing of methanol to oil molar ratio until it reached the optimum conditions. Then the yield of the methyl ester increased as the catalyst loading increased. From the study, it shows that 118 minutes is the best reaction time for the methyl ester production using the KFCRWFE2O4 as the catalyst. Then the next optimization study is the Anova analysis. Anova is used to examine the variance in the result induced by each parameters in relation to the overall variations. If the F value is 6.3589, the parameter has the significant impact on the response. If the F value is 3.6824, it has a significant influence. The P values are a method to identify each variable significance and shows the relations between each independent variable. From the study, MO molar ratio has the smallest P if compared with the other two parameters. So it shows that it has the significant parameters on the production of methyl ester, followed by the catalyst loading. Then the biodiesel produce also undergo the FTIR analysis. FTIR was employed as a fast and reliable analytical technique for the quantification of the fatty acid methyl ester content in the produced biodiesel. From the table shows here, it shows the frequency and the functional group that present in the biodiesel produce. In conclusion, KFCRWFE2O4 have the outstanding catalytic performance for the trans-esterification reaction. The optimization study indicates that methanol to oil molar ratio is the most significant parameters, followed by the catalyst loading and the reaction time for the production of the methyl ester. The strong basicity of the new catalyst demonstrate that the KFCRWFE2O4 catalyst has promising applications in the biodiesel industry and contribute to a waste-free world. So here, our team would like to acknowledge the support given by Ministry of Education, Unit 10 Board 2025 grant, Mineral Research Center, Institute of Sustainable Energy Unit 10, and Putrakat UPM. That's all from me. Thank you so much.
Thank you, Lim. So I open to the participant for Q&A. Any questions?
Hi, morning, John. I have one question here to
Okay, Dr. Lim.
Lima. Yeah. Very. Thank you for your presentations, Lim. Just want to ask about the. Do you conduct any leachings or stability tests for the catalyst? Because I know that those active potassiums, calciums, and ions phase is quite soluble during the transesterification process. Okay, this is the questions from me.
Sorry, your question is not clear. I cannot hear clearly. Can you repeat again? So sorry.
Okay, I repeat again, sir. I just wanted to know whether you have conduct any leaching test for your catalyst or reusability test for your catalyst.
I did for the reusability before. It can be reused for 2 times. After second time, the how to say, the performance of the catalyst will drop actually, and it cannot produce any meta ester.
So, do
Okay.
you know what's the reasons of this short reusability?
Maybe due to how to say, because how to say, the potassium maybe is not how to say, not attached. It's not strong. I don't have any strong attachment to the catalyst. Maybe due to the maybe low attachment during the purification, it will be how to say what how to say, mix into the methanol, like how to say, leaching during the just esterification. This is how to say, one of the part that need to be improved.
Okay, thank you.
Okay, thank you, Dr. Lee. Any other questions or suggestions? Okay, Dr. Lim, I have one thing that I want to clarify with you. Is about the yield, right? What's the yield that you get? Because this is the you use this is the normal biodiesel, right? Is it normal biodiesel?
Yes, no,
You produce glycerol, is it?
glycerol also
Okay.
produced during this process.
Okay, thanks. So any other questions? If no, thank you, Lim, for great presentations. So we move to the next speaker, our invited speaker. So we are very fortunate to be able to invite Dr. Muhammad Hafiz Ahmad, right, to share with us a topic entitled Synthesis of Butylate Hydrotoluene Ligands Conjugated with Gold Nanoparticles is an antioxidant activity and cytotoxic effects against cancer cells. So, Dr. Hafiz, the floor is yours.
Okay, thank you, Dr. Juan. Assalamualaikum and good morning to all. My name is Muhammad Hafiz bin Ahmad from Nanotechnology and Catalysis Research Center, NanoCat, University Malaya. For today's session, I would like to share my research work entitled Synthesis of Butylated Hydroxytoluene Ligands Conjugated with Gold Nanoparticles, Antioxidant Activity, and Cytotoxicity Effect Against Cancer Cells. My research background. For your information, the presence of free radicals in our surrounding was discovered as approximately 50 years ago. The uncontrolled oxidation metabolism inside human body, UV light radiation, X-ray radiation, and air pollution may produce free radicals and other reactive oxygen species as byproduct. Overproduction of such free radicals can cause oxidative damage to biomolecules, example lipids, protein, DNA, eventually leading to many chronic diseases such as heart disease, cancer, diabetes, aging, and other degenerative diseases in humans. What are free radicals and what is the relationship of free radicals and cancer? Free radicals are byproducts of oxygen used by every cells in human body. body cells use oxygen to transfer energy stored in food to a usable form. Unfortunately, at high concentration or overproduction of free radicals, they become hazardous to human body because of free radicals are like robbers which are deficient in energy, and they attack and snatch energy from other cells to satisfy them. Here are some examples of reactive oxygen species or known as oxygen center free radical. To overcome this problem, antioxidant or known as anti-radical helps to prevent cells from damage by scavenging free radicals. Antioxidants. Antioxidants are molecules which can safely interact with free radicals and terminate the chain reaction before any damage is done. They will convert free radicals to harmless molecules by donating their electron. Antioxidants can be classified into three groups. They are natural, synthetic, and metal antioxidants. Here we will see how the development of nano antioxidant from past few decades until now. The researchers start with the finding of organic molecules as antioxidant agent. Then inorganic chemists also start to develop antioxidant agent by using metal element. These two strategies are classified as traditional strategies. Then, the discovery of new generation of antioxidant has been started last decade by the combination of organic and metal antioxidant to produce nano antioxidants. Here, this is the list of examples of nano antioxidant with their biological activities. Due to the potential of these nano antioxidants, they give inspiration to develop new nano antioxidant with good potential as antioxidant as well as can act as anti-cancer agent. In my research, I choose butylated hydroxytoluene and gold nanoparticles because of their ability as antioxidant agent and important role in clinical treatment. BHT. BHT is well-known synthetic antioxidant, was patented in 1947 and was approved for use in low concentration by US FDA. It is used as preservative and stabilizer in several industries such as food, pharmaceuticals, and cosmetics. Here's some example of BHT derivative used in pharmaceutical industry. As we can see here, the parent structure is BHT moiety. The reason why I choose gold nanoparticles because gold nanoparticles do not oxidize or burn in air, inert, easily stabilized by addition of ligands, low toxicity, and biocompatible metal. Because of these properties, gold nanoparticles have been used for several biomedical applications such as anti-arthritis, anti-rheumatism, and anti-cancer. Here's some example of gold nanoparticles used in pharmaceutical industry. Next, among all different types of disease, cancer remains a leading cause of mortality worldwide and extremely increased over the years, reported by World Health Organization (WHO). In Malaysia, the huge numbers of new cases with breast and colon cancer are the most common types encountered reported by Malaysian Cancer Association (MACNA). To prevent the cancer disease, researchers have been used phenolic compounds to treat cancer due to their tremendous ability as free radical scavenger, and one of them is BHT. Unfortunately, the consumption of BHT causes the adverse effect to human health. For instance, researchers have produced Park-Davis inhibitors to improve activities of COX-2 inhibitors using isothiazolidine derivative containing BHT antioxidant moiety. Inspired by this result, our strategy is to functionalize the antioxidant ligands onto the surface of antioxidant nanoparticle could produce excellent nano antioxidant compound as anti-cancer agent. The functionalization of sulfur-containing BHT ligands on gold nanoparticle surface is novelty of my research. Nanoparticles will enhance antioxidant activity and minimize the toxicity of ligands. For my research methodology, it consists of 4 steps. Step number 1 is synthesis of ligand using acid catalysis reaction. Step number 2 is synthesis of gold nanoparticles using Turkovich method and characterization of synthesized nanoparticles using UV-Vis, XRD, SEM, and TEM. For step number 3 is preparation of nano-antioxidant, and step number 4 is biological activities of ligands and their corresponding nanoparticles. In this research, 8 BHT ligands were successfully synthesized using acid catalysis reaction. 4 of them consist monosubstituent of BHT, or I label it as a group A, and one group of 4 ligands consists of disubstituent of BHT, and I label it as a group B. From these 8 compounds, I take compound 2A from group A and 2B from this group to briefly discuss about their structure conformation and functionalization with gold nanoparticles. Okay, here the data to support the structure conformation. For this molecule for both structure, I got from liquid chromatography mass LCMS, and then from the molecular weight, I got the information about the molecular formula of each ligand. Then for the IR spectra, it gives the information of functional group contained in the structure. And this is the NMR spectra for both compounds. Based on evidence from all data, they will strongly support the structure conformation of each compound. Next, this data shows antioxidant activity of BHT ligand before functionalization with gold nanoparticles. All compounds show the potent activity compared to BHT, except compound 4A and 5A. Among them, compound 2B is the most potent compound with 47.9% decrease of IC50 value than BHT. And all compounds were tested for their cytotoxicity in comparison with BHT against 2 different cancer cell lines, HT29 colon cancer and MCF7 breast cancer, as well as non-tumorigenic cells for their selectivity index. All compounds show promising cytotoxicity effect against 2 different cancer cell lines. And again, compound 2B shows higher cytotoxicity effect against both cancer cell lines and higher selectivity compared to standard drugs, tamoxifen for breast cancer and 5-fluorouracil for colon cancer. And for the characterization of gold nanoparticles, UV-Vis spectrum shows the absorption peak of gold nanoparticle at 520 nanometers. This peak gives the information that gold nanoparticles that are synthesized in spherical shape and 10 to 20 nanometers in size after compare with literature. And here, as we can see here, this is the typical XRD pattern, and signature peaks of gold nanoparticles were observed in this spectrum. For TEM image, the image of synthesized gold nanoparticles shows the particle size in the range of 10 to 20 nanometers. The size distribution of my synthesized gold nanoparticles show the particle size is around 10 to 13 nanometers. And then the high resolution image of lattice range of gold nanoparticles shows the crystallite size is 0.233 nanometers, almost similar with the literature. For the same image, the image of gold nanoparticles show they are formed in nanosphere shape and agglomerate by each other. Based on all data and comparison with literature, gold nanoparticles that I synthesize are 10 to 20 nanometer in size and nanosphere in shape. Okay, next. Okay, here is 8 new nanocomposites were synthesized to increase antioxidant activity and cytotoxicity effect by the assembly of antioxidant ligand linked on antioxidant nanoparticles. This is the illustration structure of my nanocomposite. Several tests were used to indicate the functionalization of ligands and on gold surface is successful. First, the color changes. As we can see here, the color changes of gold nanoparticle was converted from wine red color to purple after functionalization. It gives the information that it shows that the interaction between ligands and gold nanoparticle occur. For stability tests, nanocomposites show good stability compared to gold nanoparticle after 3 days. And next, the temp image show that the particle size is still remain the same after functionalization. As we can see here, the size distribution of nanoparticle size still in the range 10 to 13 nanometers. For the same image, the image showed the functionalization of ligands on gold surface does not affect the particle shape. The shape still remains in nanosphere shape. Then, the EDX analysis proved the presence of ligands on the surface of gold nanoparticle. It showed the presence of all elements contained in ligand. For FTIR spectrum, it showed the attachment of ligands on gold surface. Before functionalization, the terminal thiols of mono substituent of BHT appear at this peak, then disappear after functionalization. But for disubstituent of BHT ligand, they have no thiol peak because they don't have the terminal thiol at the end of the ligand. In this case, the confirmation of functionalization for disubstituent of BHT ligands is supported with EDX data and biological activities. So, all data in this part show that the functionalization of ligands on surface of gold nanoparticles was successful. Next, then, all data are supported with antioxidant activity result to show the functionalization of ligands on gold surface is successful, not only for mono BHT ligands, but also dimerization of BHT ligands. All nanocomposites show strong antioxidant activity with lower IC50 value than standard gold nanoparticle, except nanocomposite 2A, nanocomposite 4B, and 5B, which show moderate activity against DPPH radical. Nanocomposite 5A show greater inhibition with 66.1% decrease of IC50 value compared to gold nanoparticle. And then for cell viability, 8 nanocomposites were evaluated for their cytotoxicity in comparison with gold nanoparticles against two different cancer cell lines, HT29 colon cancer and MCF7 breast cancer, as well as non-tumorigenic cells for their selectivity index. Most of the nanocomposites show good cytotoxic effect towards cancer cell lines and less toxicity towards normal cell. Among them, nanocomposite 2B display the highest cytotoxicity effect on both cancer types and show superior selectivity index in colon and breast tissue. Then, based on all works that I have done, I conclude that 8 sulfur-containing BHT ligands were successfully synthesized, 4 monosubstituent of BHT and 4 disubstituent of BHT. The novel nano antioxidants was successfully developed as a new wave of antioxidant therapies for treatment of disease involving oxidative stress. The nano antioxidant improved the antioxidant ability of nanocomposites as free radical scavenger. Functionalization of ligands with gold surface increased the selectivity of nanocomposite and their ability as useful and promising anti-cancer agents. Here I want to acknowledge University Malaya, Nanotechnology and Catalysis Center and Faculty of Pharmacy, University Malaya, and also Ministry of Higher Education for research grant and my PhD scholarship. Before I finish my presentation, I would like to express my biggest gratitude to my former PhD supervisor, Dr. Wajid Abdul Hadi, Professor Dr. Nur Saada, and Dr. Najiha. And special thanks to my small organic chemistry family in NanoCat for being a part of my life during my PhD journey. And that's all from me. Thank you.
Thank you, Dr. Hafiz. I'm pleased to call you Dr. Hafiz. Okay. I think Dr. Hafiz worked very hard in NanoCat. So any questions or suggestions for Dr. Hafiz?
I have question.
Okay, yes, Shabila.
Thank you, Dr. Hafiz, for your clear presentation. I have one question. how can we know the size of our antioxidant? What I mean is that if we modify any antioxidant, functionalize with any metal, then we can get nano antioxidant. Is there any possible that we might not get the nano size?
Okay. The most important is, if I'm not mistaken, during my PhD research, the most important is your ligand concentration. The ligand concentration affect the size of nanoparticles. For example, I using the Turkovich method for synthesis. I using reducing agent. That method is a standard method, so it directly give the size that I want. So in your case, maybe you need to try to optimize your method to find to find the good concentration or better concentration to produce your nanoparticle.
Okay. Thank you.
Okay. Any other questions? We have another 5 minutes. Another question. Any questions? So, Dr. Hafiz, proceed with the Shabila questions. Do you observe any, because when you synthesize nanoparticle, you should form a micelle, right? Do you have any study on the CMC and the micelle and so on, so that you can produce a very regular type of nanoparticles?
Okay, thank you, doctor. Actually, I also looking for that opportunity to working with myself, and because sometimes working with only for the synthetic compounds, we are not really sure is that our nano composite will directly go to the target cell. So maybe by using my cell, or maybe we can try to combine with DNA. Maybe that will help how to make the nano composite become more efficient during drug delivery.
Okay, that's very good, Dr. Hafiz. Since you have graduated, okay, some of the small suggestions, okay. Now people are going for these what I call nanoparticles and organic molecule, but they go for these robot type. That means a small robot that can, cure cancer. That means this type of material, right? You go into the cells and have a motor and you drill the cell and also vacuum the cell and do a lot of things. Maybe you can look into that in the future research. That's the trend nowadays. No longer on you function here, function there. Those kind of research is good, but since you have graduated, I think maybe you can venture into that. That's my suggestions. Okay.
Okay,
Any
thank
other
you.
questions from the floor, participants? Okay, if no, then we thanks Dr. Hafiz for very great presentations. So we move to our next speaker. So we have our next speaker. This also very renowned professor, Associate Professor Suresh Sagadewan, and he is going to share with us a topic entitled Enhanced Photocatalytic Activities under Visible Light of GC3N4 Alliance Zinc Oxide Composite Material. So, Prof. Suresh, the floor is yours.
Thank you, Dr. Juan.
I can see your slide. Okay.
This is a full screen mode. Can you see?
Yeah, I can see your slide. Can you what you call make into a presentation mode?
Yeah, now it's presentation mode.
It's no, it's not. It's, from our view, it's not a presentation mode.
Oh, here it is. I'm having some problem.
Okay, this is fine. Let me see.
Okay, now it's fine.
Okay, it's better. Wait, can you zoom in a bit so that it's gone now?
Okay, just a minute. Here some problems going on.
It's okay. Yeah. The screen is
okay.
Back.
It's visible, right?
Yeah. Better is better. Yes.
Can I start now? Okay.
Yeah. You're given 20 minutes and 5 minutes Q&A.
Okay, thank
20
you.
to 25 minutes for presentation, 5 minutes for Q&A.
Thank you, Dr. Juan. Thank you very much.
Dr. Rishi.
First, I would like to thank conference chairman and secretary and other committee members to give the opportunity to give a talk about on fabrication and physical-chemical characterization of graphite carbon nitride with the zinc oxide composite with enhanced photochemical activity under the visible light. This was done by one of my master students. She did this work and published the paper in optical materials. We performed only for the photochemical activity of this composite material. My outline of this presentation, I'm going to talk about the introduction about photochemical activity and what is the objectives of this work and how to prepare this sample and resultant discussion, finally conclusion. The introduction, the modern science and technology have made the life of human beings very comfortable, but at the same time, they have caused the demand for energy to increase. Although the conventional fossil fuels are efficiently meeting the energy demands, the rapid depletion and adverse environmental concerns are creating panic. So these issues have prompted the research for green and sustainable alternative energy conversion as well as energy storage devices. In the recent years, the increased interest with nanocomposites due to their high surface area with supportive physical-chemical properties like thermal, mechanical, electrical, and optical, electronic, and sensing catalysis. The photocatalyst technology offers excellent potential for this complete removal of organic and other biological pollutants in environmentally friendly and sustainable means where the final outcome is without the involvement of greenhouse gas emission. You can see the current scenario, the depletion of non-renewable energy resource and pollution need to utilize the renewable energy resource for greener environment. So the solar energy is the most powerful renewable energy resource, and then photocatalyst needed for harvesting solar energy. So therefore, the high performance of nanomaterial as a photocatalyst to increase the surface area to volume ratio. And what about the properties of nanocomposite? When you're reducing the size from bulk to nano size, you can see that increasing these following properties like surface area. If you increasing surface area, it shows the highly catalytic activity and antibacterial properties and hardness, the electron band gap, electrical properties, and magnetic properties. You can see the better catalytic efficiency due to the higher surface to volume ratio. And electrical properties, they increase the electrical conductivity. And mechanical properties improve the hardness and toughness of these metals and alloy. Optical properties, you see the spectral shift of optical absorption and fluorescence. And magnetic properties, they increase the magnetic coercivity, supermagnetic behavior. See, this is very interesting. This effect of controlling the properties of nanostructure material. There are 4 important challenges. One is the size effect. Another one is change of the dimensionality and change of the atomic structure and alloying of components. When you reducing the size, you see the size effect is modifying these mechanical and optical properties. We can tune that mechanical and optical properties when you're reducing the size, and as well as the change of the dimensionality when you're reducing the dimension 1-dimensional, 2-dimensional, or 3-dimensional. So nanostructure material becomes a 2 or 1-dimensional with respect to this phenomena, and as well as the changing of this atomic structure. The crystallites changing the atomic structures relative to the perfect crystal. And then alloying of components. The alloys of result is nanostructure material have different chemical composition. You see here the potential application of metal oxide with graphene nanocomposite. It can be used for different areas like transistors, sensor, lithium-ion batteries, energy storage, solar cell, catalytic and photocatalytic process, and non-volatile memory devices, the tunneling device, drug delivery, bioceramic, and antimicrobial coatings. You can see a lot of materials are developed in device also. You can see here, this is a gas sensor, humidity sensor, antibacterial coatings, microwave device, supercapacitors, lithium-ion batteries, high-density recording media, and also it can be used for solar cell and solar filters, transistor, and then VLSI applications and OLD, organic light emitting devices, optic lens, and optical windows. So this nanocomposite is used for the potential application in different areas. My objectives of my talk is synthesis of the sample. So we fabricated 3 samples: zinc oxide nanoparticle, and then graphene carbon nitride, and then composite, graphene carbonate composite. So 3 samples we synthesized by using this chemical precipitation method. And after preparation of the sample to study the physical chemical characterization, such as the powder X-ray diffraction, FTIR, UV, TEM, AFM, and thermal. Finally, we to investigate the performance of photocatalytic application of this prepared sample. Why graphite carbon nitride? Why we chosen here graphene carbon nitride? The reason is the graphene carbon nitride is recently fascinated researchers' interest due to its outstanding properties like low cost and non-toxicity. It is a biocompatible, and also it is a high surface area, and it is a fast.
Suresh, sorry,
Yeah.
Your slide doesn't move for quite some time too. Now you are in which slide? Yeah.
You cannot see that?
Yeah, which slide are you in now? Slide
Now?
number? Oh, yeah, okay. Yeah, yes.
Oh,
Yes.
sorry.
It's okay. Thank you very much, Prof.
Okay.
Because,
okay. Yeah, it is a high surface area and it's biocompatible,
Yep,
non-toxicity, low cost. So we have chosen the graphene carbon nitride with the combination of zinc oxide nanoparticle and incorporate with this graphene carbon nitride. Motivation of this work. What is the advantage? That means the nano hybrid have gained amazing concentrations owing to the potential functionality for tailor-made applications. In that view, the health and environmental influence of the graphene-based material should be carefully assessed in advance of the prospect of applications. So this taking advantage of excellent properties. You can see the graphene carbon nitride with zinc oxide composite. It is a simple preparation method and it's low cost, the excellent stability, and a high catalytic activity. So that the many groups have widely researched its capability as a photocatalyst. And synthesis of zinc oxide nanoparticle, graphene carbon nitride, and then composite. So we have chosen here the chemical precipitation method. Why the chemical precipitation method is considered to be one of the most convenient and very simple technique. The several advantages by using this method. It is a simple and rapid preparation technique, and also we can easily control the particle size and composition. Another important advantage is operated at low temperature and it's produced is energy efficient. The first we have synthesized zinc oxide nanoparticle. You can see here in the slides, you can see that the sodium nitrate solutions, the 1 mole of zinc acetate dihydrate solution was make up of 50 ml, and then 50 ml of solution of sodium hydroxide was added dropwise, continuously the stirring until we see the formation of large quantity of precipitate. The stirring was continued with this precipitate for another 18 hours. And after this period, the filter to obtain this precipitate washed with the distilled water and several times. And then we can go for centrifuge to obtain this product. The product was dried and by using at our oven at 100 degrees Celsius to remove the moisture. Finally, then grind to fine powder, and then finally we calcinate at 400 degrees Celsius. We obtain this zinc oxide nanoparticle, and then again we obtain this bulk of graphene carbon nitride. This thermal polycondensation process was followed to prepare this graphene carbon nitride. About 5 grams of melamine in the form of white powder was heated at 550 degrees Celsius for 3 hours in muffled furnace. After this period of formation of yellow powder confirms the formation of graphene carbon nitride. So this formation of graphene carbon nitride with zinc oxide composite, we've taken the equal amount of 1 gram of both graphene carbon nitride and zinc oxide were taken and mixed thoroughly with the help of ball milling technique and ethanol as a solvent for about 1 hour, so as obtained an excellent talc-like product. So finally, the mixture is collected and dried in at our oven at 80 to 100 degrees Celsius because to remove this alcohol moiety where the formation of this composite is confirmed by the presence of yellowish white product. So finally, we obtain this composite graphene carbon nitride zinc oxide composite. After preparation of this composite, then we can study this physical chemical characterization. The first one, structural properties. We using the X-ray diffraction, you can see that the comparison of powder X-ray diffraction pattern of A is a graphene carbon nitride and B is a zinc oxide and C is a composite. You can clearly see that we observe the sharp peak at 27.4 degree for this graphene carbonate sample. It corresponding to the interplanar characteristics, stacking the peaks of aromatic structure and interlayer structural peaking. But this peak infers the crystallinity of the sample. You can see the zinc oxide peaks, well-known peaks. We observe that, which means that highly crystallinity of the sample, and also the each peak corresponding to the single phase of zinc oxide, which means there is no other phase. The we obtain this purities are high. When you see that the high intensity peaks, which means that prepared the sample is have a high crystallinity nature and also high purity form. And you can see the composite, again you can see this the composite of this XRD pattern. We can observe that the graphite peak 002, which is confirm the successful formation of this graphite carbon composite. So we can once again we can confirm this by X-ray diffraction analysis. The graphite incorporated with zinc oxide incorporated with this graphite carbon nitride. And next, we studied this FTR analysis by using, you can see that figure A and B and C, the various comparison of FTR spectrum of zinc oxide and graphene carbon nitride, and then composite. From this FTR analysis, you can see this the peak at 1640 centimeters inverse 1 can be associated to the carbonated switching of vibration, the CN switching vibration, while the other peaks around 1000 to this range 1242 and then 1320 and then 1400 can be linked to aromatic of CN switching and band at 828 centimeters inverse 1 here, due to that out of the plane of bending vibration of CN heterocycle. In addition, we observed that the band at 522 centimeters inverse 1, which is confirmed that zinc and oxygen bonding. So which means that presence of the zinc oxide with this composite sample linked to the isothermal switching of vibration. Also the presence of wide band range in the range of 2000 here, the 2750 to 3500, between the range, can be due to this OH stretching of vibration from this absorbed water or moisture. So from this FTR analysis, we conclude that it is provide the information about this matching of zinc oxide and graphene carbon nitride peaks. It can be which means the successful formation of graphene carbonate with zinc oxide composite. Once again, we confirm this by using this FTR analysis. Next, the optical properties. You can see this the comparison of UV spectrum of graphene carbon nitride and composite and then zinc oxide. From this figure, we observe that the significance of redshift due to this absorption of light for this composite, and thereby indicating its photocatalytic efficiency in the visible light region. You can see that from this figure, the absorption spectrum, the maximum of absorption of the first one, A is red. You can see that graphene carbon nitride, it is a maximum absorption wavelength. We observe that it is a 480 nanometer. And then composite is a B. You can see the B, which is a black color, that it is 471 nanometer for the maximum absorption wavelength, and zinc oxide is 389 nanometer. We calculated band gap value by using the tau plot. We found, you can see this band gap diagram for this 3 sample. The band gap value was found to be for graphite nitride A, which is the black color. You can see that 2.35 electron volt, and then composite. The composite is B. You can see that B is a 2.47 and zinc oxide C is a 3.06 electron volt. So further, from these optical properties, we confirm the shift towards the lower energy region to composite indicates this composite's sensitivity towards the UV light, which in turn supports this enriched the photocatalytic activity. And next, we studied for the surface morphology of this 3 prepared sample. A is a graphene carbon nitride, and B is a zinc oxide, and C is image is composite. You can clearly see that graphene carbonate is a sheet-like structure. You can clearly see that from the TEM image. You can see that the graphene carbonated exhibiting the morphologies as similar to the two-dimensional agglomerated laminar sheet having these rolled edges, but the sheet are folded and exploited in the sheet arrangement. You can see that similarly, you can see that 10 image of zinc oxide. It's a nanorod shape with the hexagonal or cylindrical shape, which confirms this, hexadependent pattern. And then you can see the figure C very clearly. You can see that the composite, we can confirm the successful formation of zinc oxide with graphene carbonated, which means it showed that nanorods are embedded in this sheet-like morphology, and thereby indicating the sheet-like layer structure of graphene carbonate, even this composite. So finally, the sheet-like structure of composite indicates the availability of higher surface area. Why this kind of material have that higher photocatalytic activity? Because the surface area is more, so it supports the enhance the photocatalytic activity. So next we perform that AFM analysis, atomic force microscopic image. You can see here for the three sample, the A is the graphene carbonated, and B is the zinc oxide, and C is a composite sample. You can see that from this analysis, once again we can confirm this graphene carbonate is a sheet-like structure. You can see that here the first image, sheet-like topographic, which is well matched with this 10 image. And similarly, the zinc oxide topographic image of, you can see the rod-like structure in 3D view. Also, the zinc oxide sample are arranged in the rod-like manner. Maybe the C is a topographical image of composite, is a well arranged, is a homogeneous pattern at which the rods are immobilized with graphene carbonate layer and are good agreement with this TEM image. So all the physical chemical characterization which is confirmed the successful formation of these three samples, graphene carbonated, zinc oxide, and the composite. Next, we perform this thermal properties, thermal characterization, the comparison of TGTT analysis for zinc oxide, graphene carbonitride, and then graphene carbonated with zinc oxide composite. You can see the figure. This analysis is divided into the three parts. The first one is a minor weight loss, and second one is a significant weight loss, and third one is a reduced mass. You can see that at 180 degrees Celsius, the minimum weight loss is occurring you can see this 180 degree, a minimum weight loss is occurring for all three samples, which means that the loss of hydroxyl groups and water, moiety. And in the case of zinc oxide, the significant weight loss occurred in the region of 550 degrees Celsius. You can see the major weight loss of zinc oxide, 550 degrees Celsius. This can be, maybe the phase changes occurring as a prepared the zinc oxide sample. Since as prepared this zinc oxide sample also contains some amount of zinc or hydroxyl due to its contact with the water moistures, during heating, the sample attains the major weight loss to form this ursatite as a more stable form, and the remaining portion of remains the residual mass. So finally, in the case of the sample of graphene carbonitride, the composite, the significant weight loss is attained around the temperature of 450 degrees Celsius. You can see this clearly. You can see that this is a weight loss was attained around this temperature of 450 degrees Celsius, which means that the phase change of melamine into graphene carbonated. So all the physical chemical characterizations confirm this preparation of the sample and also successful formation of this composite. After we studied that photocatalytic activities for only for composite sample, because the further study is going on, we performed this photocatalytic activity of composite sample for by using 4 different organic dyes like malachite green, rotamine B, concord red, and red ink. So in the presence of UV light radiation, you can see the from figure, you can clearly see that the time interval of all dyes are 0 to 45 minutes. As some of the significant photocatalytic activity was observed only for this composite. You can see that from the table, the photocatalytic activity of malachite green and rotamine B, concord red, and red ink solutions. You can, from this table, you can clearly see that it can be observed that the composite has the activity against all the dyes and solution tested. It is getting reduced with increasing the time period. You can see this table, you can clearly understand. Because the reason is the loss of occurring in the number of active catalytic sites. Further, among all the reactor tested, you can see that we observed the highest absorption for only, you can see that red ink solution, the dye, you can see that you can see from the table, it is only for highest absorption solution, followed by other dyes like Concord red, malachite green, and rhodamine B. And next, the photocatalytic efficiency percentage of individual reaction was calculated, and the results are shown in the figure. You can see the values are so tabulated. The degradation efficiency of malachite green, rhodamine B, Concord red dyes, and red ink solution. You can see from the table also you can see the percentage. From this graph, you can clearly see that we can observe that the highest photocatalytic activity was observed by the malachite green. About the 97.24%. It's followed by rhodamine B is 82.37%, and Concord red is 70.05%, and then last one is a red link is a 46.9%. So this from this result, the enhanced activity of graphene composite, graphite carbon nitride zinc oxide composite towards this organic dye degradation due to its interfacial structure, which helps for this reduction of recombination rate and photo-generated electron and hole pairs. The next is, CT by C naught versus time. You can see that graph. The figure shows that CT by C naught is strongly increased by the irradiation time. And so the changes in the concentration of 4 dyes along with the time or recorded, you can see that it can be observed from the figure. The photo degradation of all the tested dyes and solutions are extremely slow. You can see that the red ink shows 0.53 in the dark, and 0.29 Concord red, and rhodamine B is 0.1763, and malachite green is 0.0276. So this is a visibility elimination of this for this composite. And next is from this figure, we plot the graph between this time versus land CT, the kinetic studies. From these kinetic studies, we calculated this R squared value. That means, the rate constant were calculated based on the slopes of each dyes. The values of R squared found to be in the range of 0.9705 for malachite in green, and 0.9839 for rhodamine B, and 0.98 for Concord red, and 0.9866 for red ink solution. So this is a schematic diagram of for this composite. From this graph, after receiving the visible light, the electron hole separations occurs simultaneously on composite. The electron moves to the conduction band and leaving the holes H plus on this valency band. So this process significantly reduces these electron hole recombinations occurring in this composite. So this electron in the conduction band of the catalyst get trapped easily by the surface absorbed by the molecular. The oxygen spices to form these superoxide radicals, and also is further responsible for this involvement of degradation reaction with that of adsorbed dyes like malachite green, rhodamine B, Concord red, and RX solutions, anything. So therefore, from the the photocatalytic reactions by this composite occurs through the well-known mechanism of visible light driven electron excitation from valency band to the conduction band. Also by production of reactive intermediate free radical spaces, where all this happens sequentially to degrade these 4 dyes like malachite green, rhodamine B, Concord red, and RX. Finally, summary of this my talk. We indicate the successful fabrication of this graphene carbide zinc oxide composite. The following physical characterization of this synthesized sample by making use of various instrument techniques like FTIR, UV, TEM, AFM, TGDTA. It was tested for this composite and as well as zinc oxide and graphene prepared sample. The photocatalytic performance of investigated towards this degradation of organic dyes. So further, this photocatalyst can be explored for successful decomposition of organic dyes and other industrial pollutants in sustainable way, where zero emission are produced as part of this reaction. So I Recorded my sincere thanks to all my collaborator. This work done by one of my master students. She's graduated master. Completed her project with this work, so we cannot do for further this due to this time constraint and due to this funding issues, so we cannot go for individual sample for this photocatalytic activity, and then maybe we can do for the future analysis for stability and other characterizations. We can try only for the different types with perform this photocatalytic. So thank you for your patience and thank you for listening me. Once again, I thank Dr. Juan.
Hi. Okay, thank Prof. Suresh for very interesting talk on photo activity. So I open to the participants. Have any questions? Prof. Suresh.
Yes.
It is very interesting on the thermal analysis.
Yes.
I saw that the zinc oxide, right?
Yeah.
Totally, completely degraded.
Yes.
I just wonder, right? The zinc oxide, I mean the TG. You are talking about that. How can be it's a curiosity. How it can become totally gone? Huh?
Yeah, we observed that, in the case of zinc oxide, only occurred the 550 degrees Celsius due to the phase changes occur, not completely. Can you hear me, right?
Yeah. But this is a weight loss, though. It's not a DTG. It's a weight loss. It's not. You look at the TGA diagram.
Yeah,
it's
TGA.
Loss.
Yes.
It's a weight. It's not a thermal, endothermic or isothermic thermal.
No. It can be. Yeah, it will be done by DSC, differential scanning calorimetry. Yeah.
But this is weight, That means your zinc oxide totally gone, Then zero. No more.
Yes.
No more.
Yes.
Just curious on this, Prof. Suresh. Yeah, you can go back to your TGA and you look at it again. Just wonder why it become gone. Like say, for example, I have zinc oxide. If I burn until 800 degrees C. At least I have zinc. I still have zinc.
Can you see my slide?
Yeah, I can see your slide is moving.
Moving, right?
Yep.
Yeah.
For the TGA. Yes. This one, the zinc oxide become gone. Totally. The zinc also gone. Zinc is a metal, though.
Yes, metal. Yeah. Yep. It will go for around 800 only. It remains residuals, but it will changing this major weight loss occurred at 450 degrees Celsius. You can see this 400 to 600. Can you see Can you see that, right?
Yep.
450. You can see that 450. The major loss. Yeah, major losses occurred. Weight loss occurred. The zinc oxide is 450 degrees Celsius. After 550, you can see that 550 phase will be changed. The phase can be changed occurring this prepared zinc oxide sample.
Yeah, the phase can be changed, but the weight cannot change.
Yes, phase only change. Yeah.
But this one is the weight. You get the y-axis, x and y. Okay, x is the temperature. Y is the weight. That means, let's say you have 1 gram of zinc oxide. If you burn at 800 degrees C, it becomes 0. Or you have 1 kg of zinc oxide, you burn until 800 degrees, you have nothing there. You go back and see, nothing is left,
Yeah. Yes,
that's a bit of curiosity, though. It's a phase changes, I understand, because phase changes,
Yeah, I got your questions. Yes, I got your questions. Already we done. Yeah, we checked that, rechecked, and also maybe I can. Yes, maybe I can try. With,
you understand me, right? Because the face understand, it's like titanium have anatase and then the face is there, but the weight is not gone, because the zinc is a metal. It's not organic.
Metal.
It's like even the GCN is
carbon.
Organic.
Carbon easily bond. Yeah, carbon is easily bond.
Still can become CO2 and NO2 become a gas, but zinc oxide it cannot become a zinc gas. You understand me, right?
Yes, it's metal oxide. Metal oxide.
So okay. Thank you for your discussion here.
Thank you.
For other participants here? Any other questions? I would like to thank Prof. Suresh for a very, very interesting talk. Okay.
Thank you so much.
Prof. Suresh also attached to a NanoCat. Unfortunately, he is not able to join us for pandemic. Okay.
Yeah, pandemic situation.
Hopefully, you'll be here in Malaysia.
Please, all of you, be safe and take care of your health and take care of. Take care of yourself, okay, during pandemic situation.
Yeah, thank you, Prof. Suresh. Okay, so we still can do some minor research. I think
sure.
lab also be in a lockdown situations. Okay, If no questions, thanks again to Prof. Suresh. I would like to announce the best presenter, okay, for our two presenter, of course, not excluding the invited speaker, because the invited speaker are the best presenter already, okay? They are very, very best presenter. So this is for our, normally for students. There are two participants here, Miss No Adina and Mr. Lim Hong Hua. Okay, so after very close, the mark is very close. Okay, so the final one is the right to announce Miss No Adina Shahira is the best presenter for this session. Adina, can you turn on your video? Yeah, Adina. Congratulations. Okay, congratulations.
Thank you so much.
Yeah. You have something to say?
I would like to say thank you for the opportunity, especially from my supervisor and also my previous assistant supervisor to Dr. Muhammad Supri Mastudi and also Miss Nona Bihafauzi for giving me the insightful story about the biodiesel, and also thank you very much to all the panel as well. Thank you so much.
Thank you very much, Dina. Congratulations again. Okay. Hopefully you can work. Okay, this is not the end, it's the start. Okay, so work harder and get some more interesting result. Okay. Now I think come to the end of our sessions. We have a networking session at 12:10. You can go to the side left-hand side. You have a networking what you call icon there. You can click and you can network with our what we call our presenter and our speakers. So this come back at 12:35. We have this what we call keynote sessions, by Professor Dr. Azhar Arifin. It's again it's about organics, carbonyl-based thermal in organic light emitting diode OLED applications. So with this, I would like to end these sessions. Thank you very much for your participations and for your time. See you again. Bye bye.
Doctor.
Yes.
Before.
Oh yeah. Sorry. I always forget this one. We have a photo sessions. Please turn on your video. Means your camera. Turn on your camera.
Dr. Lee is not here.
Prof. Suresh. Yeah. Now I can see.
My background is very bad. Yeah, that's why. Okay.
It's okay.
Dr. Laili.
Dr. Laili, Dr. Laili,
It's okay, Dr. Juan. My parents not allow me.
Oh, okay. Will not allow you. Okay, that's fine.
Okay.
Anyone is here?
Dr. Lee.
Dr. Lee Hui Woon, not allowed also. I won't do the makeup and so on, ladies. Okay.
It's okay lah.
Okay, so we can proceed. I think.
Okay, 1, 2, 3. Okay, wait for another one. Maybe we can have a freestyle.
Freestyle, okay.
Yeah, freestyle. Yeah. Okay, wait. 1, 2, 3. Okay, thank you.
Okay, thank you and stay safe, everyone. Yeah, bye bye.
Thank you.
See you again.
Bye.
Thank you.
Congrats, Indina.
Thank you so much. Congrats to Mr. Lim. Thank you, Dr. Hafiz.